So welcome to the morning session, and it's my pleasure to introduce Professor Alberto Verjovsky. So he will talk about loop group and variety and loop group.
So again, I thank the organizers. Back to step number one. I'm sorry I'm not there, but I'm there in spirit. So this is the title of my talk, and it's showing work with Juan Manuel Burgos. So I take a system of maps, algebraic maps, indexed by a directed poset, and where each map, which is each Vj is an algebraic variety, will be compact, or will be of the same dimensions as Fij are algebraic maps. Here's an example and maybe a motivation. If you take a rational map of degree d greater or equal than 2, which is a very important object from the dynamical system viewpoint, as you know, you have the Urea set, the Fatou set, the Mandelbrot set. I mean, Fields metals like Yokos and Macmillan. It's very interesting. So the thing to do here in this particular case is to take this system of the same map, F, and you take the inverse limit of these maps. And then when you have this space, this limit inverse is the space of sequences in the product of n times the projective line. Our sequences satisfying this condition. And this is the space of Bauer orbits of F. And the L is just chosen carefully because L will be a lamination, but it's a singular lamination. So you take a point in this inverse limit, considered as a sequence. So it is regular if there's an neighbor U of the initial point whose pullback along the Bauer orbit is eventually univalent. That means that from there on, the inverse limit of a disk is a disk, a disk, a disk, a disk. This is interesting because that means that if you take the projection onto the first coordinate, this will give you a map from L to the projective line, such that generically the inverse limit of a point is the Cantor set, and it will give you a beautiful lamination. So laminations are topological spaces. I will consider only in general compact, mostly, and are topological spaces that are locally modeled on a disk. Well, n-dimensional lamination is a compact space model in local model is a disk cross a Cantor set. And the gluing maps preserve the plug. So it's like affiliation, except the transverse structure is Cantorian and not a manifold. So that's a lamination, and laminations appear all over the place. I told you dynamical system was used by Dennis Sullivan to obtain great theorems by Misha Lubitsch, Yair Minsky, and so that's the motivation of my talk. But the type of laminations we consider in these papers are solenoidal manifolds. It's a name coined by Dennis Sullivan. These are Hausdorff topological spaces equipped with a covering. This is what I just said, UI, of the form a disk, n-dimensional disk, times a transversal, which is a holomorphic to the Cantor set. And you have, just like affiliation or affiliated manifold, you have changes of coordinates, and you can impose on these changes of coordinates different regularity conditions. For instance, if you're in dimension 2, you may suppose that the leaves are Riemann surface, and the changes of plaques are actually holomorphic maps. And actually, you can do everything you can do for manifolds, you can do for laminations. In the leaf direction, you do differential geometry, symplectic geometry, complex geometry, whatever. And the thing you require, the transverse direction to be continuous, or sometimes measure preserving or some quantity. So this is the object we are dealing with. But there's a canonical solenoid, which is the universal covering, the algebraic covering space of the circle. So we take the circle as a set of unit complex numbers, and we consider the set of all coverings of S1 to S1. Every covariance of the form Z equals to Z to the power n, and the integers n are form a directed set on the division, and then you have an inverse limit of this, and it's a beautiful object which is a solenoid, for instance, and here it is described. And this is actually very interesting because since coverings of S1 are not only covering maps, are actually homomorphisms, groups of homomorphisms, C goes to C to the n. This inverse limit is a one-dimensional connected space that looks locally like the Cantor set across an interval, and actually it's an abelian group. It's an inverse limit of compact, is a compact abelian one-dimensional group, and therefore by Pontryagin duality is the dual of something in the rationals. Well, it's actually the Pontryagin dual of the rationals, and it's a beautiful object. And the essential theme of this talk is like a regla de tres. I don't know how to say. A rule says that a circle is a one-dimensional connected abelian group, and I want to use a different abelian group. So for me, I will replace the circle by a solenoid. It's a diffuse version of circle. Diffuse because it looks like a Cantor set cross an interval locally. And so the theme of my talk is to consider, instead of loops, for instance, to consider solenoidal loops or etc. So this is, and this is just justify the title Adelic, because I will tell you. So you have canonical projections from these. These are actually characters. This S1 is an abelian solenoidal group that covers every one-dimensional compact solenoidal group by Pontryagin duality. And so this is actually the profinite completion. And since there's a canonical map from these spaces of sequence, you consider the first coordinate. That's a homomorphism up to the circle. And the kernel is the profinite completion of the integers. And that's actually the connection with Adel of the name justifies. Here's a topological description better from a dynamical system viewpoint. This one-dimensional compact solenoid, fibers of the circle is what just said. The kernel is a profinite completion. You have everything is in this sequence. So this is a Cantor set, but one way to look at it is actually is a fiber bundle. It's actually a principal fiber bundle over the circle with fiber Cantor group. I mean, in high school, they never teach, well, sorry, university, they never teach us that Cantor set is a group, which therefore is homogeneous. But so this is a principal fiber bundle over S1 with fiber, the provided completions of the integers. And this object is beautiful.
So presumably this looks like a bundle on the circle. The gluing, we need to glue, come back, and this is presumably an automorphism of the group that is a Cantor set.
Exactly, it's the adding machine. It's the adding machine, perfectly well. I would describe it here.
Okay,
it's actually the suspension or translation by one in this provided completion. Thank you very much.
Perfect. Okay,
it's a suspension. So you have, but actually there's more than that. So it's actually the Adel group of the rationals divided by the rationals. And that justifies just the name what I want. But what I want to say, I want a solenoidal group, one-dimensional. So to me, it makes no difference. Think of the circle or think of a prism. I could take the diadic solenoid of the Toric Varieties, anything like that. And the idea is to consider loop groups, consider et cetera, et cetera, et cetera. This is the object of this talk. But anyhow, this is exactly what you said precisely. You take the profinite completion of the inches multiplied by R and take this translation, this action. So in the R direction, you translate by N or minus N. And in the profinite completion, you add an integer. So this is an action of the integers on this product. If you take the quotient, you get the solenoid. And it's a beautiful object, therefore, but Well, there's a so it's like a solenoid that actually is you may think of this as a solenoidal Lie group. And the connected component of the identity is a dense leaf. So this solenoid is foliated by copies of the real line. And they are actually translates of the connected component of the identity, which is a copy of R densely embedded in this solenoid. And this is so we have that this solenoid is a compact connected abelian topological group. And well, what I just said is foliated by one-dimensional leaves. And you can actually consider like, it's just like a circle. You can do all differential geometry. You have a Riemannian metric. You have a flat metric. The leaves are flat. Well, you can do analysis on this. You can do it. So here's again the same thing. I repeat it again. This inverse limit and the foliation. So this is just a diagram explaining what I told you. That this solenoid is the principal fiber bundle of the circle, and the base leaf again is the connected component of the identity. So this I go fast because so you have a foliated space, and the question they asked me is obtained by taking the Cantor set, multiplying by an interval, and gluing. It's a mapping torus, glued by the adding machine, and that's a way of visualization. But it's important to realize that it's also a group. And actually, you know, the circle, the first thing we learn in school is that the universal cover of the circle is the real line, and the map is the exponential map. Well, here we have the exponential map also. This solenoid is covered in the solenoidal sense, which is very delicate because it's not locally connected, by this group. And so you have the exponential map, which is very useful for many things in this talk. I call it exp, capital exp, and it's this lamination can be actually thought of as the leaves of a flow by translations. And actually, for me, it's more convenient to take S1 as a multiplicative abelian group for different reasons. And actually, here I recall you that the profinite completions of the integers is this part here is the Cartesian product of all the p-adic integers. And so it's a countable product of Cantor sets. But countable product of Cantor sets is a Cantor set, no problem. And so you have this canon. So I'm describing here the geometry of this thing. And that is just to justify why I use the name Adelic. I use it because it actually, the adels are embedded in this construction. Well, actually, I can do this inverse limit construction with any group that pleases me. And so if I take the multiplicative group, the one-dimensional algebraic group C star, and also I can take the semi-group C, and I take the maps Z goes to C to the N. For this case, of course, it's a branching covering with branching at the origin. But for this case, it's a beautiful object. So you have this inverse limit, and the bonding maps are powers, Z goes to C to the N. And therefore what you get, it's a beautiful object that I call the solenoidal, whatever. It's actually a lamination. It's a complex solenoidal Lie group. And it's sort of like, because C star as a Lie group is R plus cross the circle by Pontryagin duality. Well, this actually, this object here will be actually equal to R cross or R plus, depending if you multiplicative, R plus cross the previous solenoid. So it's like C star, but it's a solenoidal. This is a solenoidal version of C star, because I'm talking about toric varieties, proalgebraic toric varieties. It would be important to me to consider, instead of C star to the N, an action of C star to the N, actions of this. And well, let's name this C star Q. The Q is because this is actually the Pontryagin dual of this of the rational cross R. So this is a nice name. So this is solenoid. and fibers of C star. And here is the same thing. It's also a fiber bundle over C star with fiber Cantor set. Well, the Cantor set is actually a profinite completion of the integers, but I like to think of it as a principal bundle. I mean, even if it's totally disconnected, it's useful to think of that. And so well, what about a topological group is called an abelian Pauli group if it's isomorphic to a closed subgroup of a product, possibly infinite, of finite dimensional real abelian Lie groups. And this class of groups is closed on the formation of products and closed subgroups, and well, there you have one. The n-dimensional algebraic profinite torus is the profinite completion of this algebra. So you take the algebraic torus of dimension n, the product of C star n times, and you take the set of all covers of that, finite covers. And the set of all finite covers are actually, the covers are actually automorphisms, epimorphisms, and therefore the inverse limit is a group, and that's what we call the same C star to the n. So this is the diversion, the solenoidal or adelic algebraic torus. And of course, we recall now that, now this is, one simple lemma tells you that these things actually factors as that. That's because you can choose a cofinal intelligent set of covers of the torus to it. Now, let's recall that a normal toric variety X of complex dimension n is, I always consider normal things, is a normal projective variety which has a holomorphic action of C star to the n with an open principal orbit by holomorphic to C star to the n. And it follows from this, since X is compact, that if you subtract this principal orbit, you get a divisor, which is invariant on this action. This is called the toroidal division. And this is stratified in a finite number of strata, which are projective subvarieties invariant on the action. The classical example I will draw is the projective space, where the divisor is the divisor are the hyperplanes, the coordinate hyperplanes, and the complement of the hyperplanes is C star to the n. And exactly this is the definition: a normal complete toric variety defined over C of dimension n. And if you take X like that, and you take a connected branch cover such that the divisorial part of the branch locus, namely the complement of this is the complement of the principal orbit, is contained in a union different, then F is a toric covering. Toric coverings are important because I want to take the inverse limit, not just of any branch coverings, but actually toroidal branch coverings. And this theorem established that this thing, that if you take the inverse limit, that every branch covering can be, any branch cover of this type is also a toric variety. And therefore, we are going to take the inverse limit of that. Well, this is the same thing. This is important because what I want to take is a family of branch coverings and take the inverse limit. But let's go to the well, and actually these proalgebraic toric varieties are solenoidal manifolds with singularities. I will describe it a little later, that have a principal orbit, have an action of this solenoidal group, abelian solenoidal group, with a principal orbit, and the complement is a very interesting object. I will continue that. Perhaps the best thing to do is the canonical example. This is the canonical example. Forget about all this. If we understand this, we understand everything. So you take, we take the family of all covers of toroidal covers of the projective space. They are all of this form, are monomials dictated by n plus 1 matrix. And if you take the inverse limit of this actually is very interesting. You take CPN, the principal orbit of the C star to the N action is the complement of the hyperplane, the coordinate hyperplanes. And therefore the fundamental group is Z is the free group of rank N, Z to the N. And therefore the set of all finite coverings correspond to also lattices of this. It's a complicated directed set, but actually I can actually consider only covers that have only one factor, Z1 to the N, Z2 to the N, and that will be that's the canonical example of what I'm talking about. And of course, you can now, fortunately, will be singular, and the singularities are complicated, but not so much as I would hope to. So let's start by something more humble in which you can understand. So we take the project one-dimensional, the projective line. So you have C star, the complement of the North Pole and South Pole, in point at infinity and 0, and you take the inverse limit of these maps. Observe that if we remove the origin and the point at infinity, this is a beautiful branch coverage. We get C star to the N. We've got a regular lamination. But if I include 0 and infinity, this branches tells me that this has a singularity at 0 and infinity, and the structure will look actually like the cone up. If you take the unit circle, it lives under this covering like the solenoid S1Q. And this manifold, therefore, will look like the suspension of this solenoid at 2 points, at 0 and infinity. So apparently these singularities are horrible, but not so horrible. It looks like polar coordinates. I mean, after all, the unit disk is the cone over the unit circle. And so this is nothing to be scared. In fact, we can do analysis on of these objects. And therefore, you see this beautiful, if you take you can divide this adelic, I call this the adelic projective line, this inverse limit. This inverse limit here is the adelic projective line. And as topologically is the cone over the one-dimensional solenoid. And it's divided into equators, solenoidal equators, which are the inverse image of the unit disk and the inverse image of the complement of the unit disk. And so you have the Pontryagin dual of, as I told you, S1 is a Pontryagin dual of the solenoid is Q. And because what I want to do is to see this, to use polar coordinates to be able to define in this horrible point, singular point, that is the suspension. I mean, it's like the cone over a solenoid. I want to define power series and do analysis in that. Well, here just tell you that in this solenoid is beautiful in some sense. That is the natural universe in which fractional power series live. So it makes sense to take power series. This is because you can the set of automorphisms of the rationals is the multiplicative rationals. So the rationals different from 0, acting by multiplication, and that is what allows us. So by Pontryagin duality, a non-zero rational number defines an automorphism of the solenoid, and therefore I can take 1 over n, 2 to the r, 2/3, etc., and define fractional powers of Q. And so you have these maps. For any rational map, you can take the power to the Q. So in the case of the Riemann sphere, the only thing you're allowed to take integer powers. So if Z goes to Z to the n, if n is negative, interchange the North Pole with South Pole, and if n is integer, it's a branch covering. But in this case, we can take, and actually they are homomorphisms. In the case of P1, they are branch coverings, they are n to 1, but in this case, they're homomorphisms. But the point is that you can take irrational powers of elements in here, and therefore we'll be able to define power series. So now we take the group of characters of C star, and this is like polar coordinates. So since the group of characters is Q, you have to do Fourier analysis over Q. So the Fourier coefficients are indexed by Q, and therefore we have to make precise what do we mean by a power series. And so this is the definition. You index by if you take an index by you number the rationals, give any numbering of the rationals, and take this sum. And if it's absolutely continuous, doesn't matter what. So it makes sense to sum over elements of Q because we want to do analysis. And so now you can define in a clear way what does it mean in the disk of radius r, solenoidal disk of radius r. Remember that it's like a cone over a solenoid. Well, you have like polar coordinates of these solenoids. And well, this is the definition. A function is holomorphic if it can be expanded in a uniformly convergent, in other words, converging on compact sets of these forms, and in 0 at 0. So it's exactly like Fourier analysis. Instead of taking z to the n, I take this to the n. It's like if you think of this like polar coordinates, r z to the n is r to the n e to the 2 pi I k. So this is exactly what it means to be well, analogously a function in the complement of the unit disk. So it makes sense to be holomorphic at infinity. And then, of course, it makes sense to speak of functions that are holomorphic on an annulus or solenoidal annulus. That is because we want to define holomorphic bundles over this projective solenoidal Adelic projective line. But if I want to do this, I want to clutch maps in the usual way. And our goal will be to get something like Picard theorem and finally the Birkhoff decomposition theorem. And so this is the definition of what it means to be. So this is a Laurent Puiseux series. And Puiseux, because Q is a rational number. This is the best universe to talk about series with rational coefficients. And actually, it's tempting because you can do this for any number field. This idea, of course, you now have solenoids of higher dimension, but so here you can speak of Laurent Puiseux series. And as usual, in complex variables, the Laurent series is defined on an annulus, and here is defined on a solenoidal annulus. No problem. And well, you can also speak of polynomial if you only sum over a finite number. This is won't be used, but it's for can take of Laurent polynomials. It's something that intervenes in the Victor factorization theorem. Well, now if I have a map from the annulus of inner radius r and bigger radius r to C star, I want to, the winded number of maps of a circle to C star, the number of times it wraps around the origin, makes sense in this solenoidal sense. But actually, because you have a map from this solenoid to S1, and you have now that in the case of the puncture complex plane, the winding number is an integer, the number of, but here is actually a rational number. It's interesting, no? So you have a solenoid wrapping around a solenoid in a rational number. There's a theorem of Schaffer, which I will look. The beautiful theorem of Schaffer says that actually maps from abelian groups to abelian groups are actually homomorphisms. And that's why you use, let's see, what is this? Well, this is the definition of the winding number. So it's the homotopy class of a map from the solenoid to the circle. Nothing more than that. Well, here is just tell you, it's a preamble to the Victor factorization theorem, Birkhoff-Grothendieck factorization. So I won't, I won't. Well, that's okay. And actually, this you see this solenoidal Riemann surface is so good that you have things like the maximum principle, you have the Liouville theorem, any holomorphic map from the whole P1Q to C is constant, and the maximum principle. And this is the theorem of Schaeffer, which is extremely useful for me. You have a compact connected topological group, and you have a locally compact abelian topological group, but every continuous map is homotopic to exactly one continuous homomorphism. And the homotopy can be chosen to preserve the identity. So this is very fundamental to me for all the, so. And now we recall topologically this solenoidal projective, the Adelic projective line is topological homomorphic to the suspension of these solenoids. Suspension points are the point 0 and infinity. And by standard facts about classification of vector bundles, we know that each complex line bundle over this is topologically equivalent to maps to CP infinity. But actually, you can prove that it's like, you see, line bundles, topological, holomorphic line bundles over P1 are classified by the Chern number, are classified by the integers. And here now they will classify by the rationals, which is very interesting. So this object has the beautiful thing that Chern classes, and well, here it's more or less is simply the fact that our maps are classifying for this is the classification. It's like the Closhin map in the equator is what gives you the Chern number. Here the equator is a solenoid, and so it's not surprising that you get the rationals. And therefore we have a topological Picard theorem. So forget about the previous, just read the theorem. The group on the tensor product of equivalence classes of topological complex line bundles over CP1 is isomorphic to Q. The rational number Q associated is the first Chern number of line bundle. And you have the usual property of Chern numbers, that the Chern number of a tensor product is the sum of the Chern numbers. But now I want to actually consider vector bundles over this projective, Adelic projective line, but of higher rank, of dimension 2, dimension complex dimension. So for that, I have to make a rigorous definition. And the rigorous definition will be by clutching two disks, whose intersection is an annulus of interior radius RR. And since we know what it means to be holomorphic, we glue them. We take this hemisphere multiplied by Cn, this hemisphere multiplied by Cn, and of the equator we clutch the map the usual way we do vector bundles. And that will be my definition of holomorphic vector bundles of any rank. Then by definition, a dimensional holomorphic vector bundle is given by the single cocycle. And we require them to be holomorphic, because we're leading towards trying to prove the Birkhoff decomposition theory for this. Grothendieck, Birkhoff, started by Birkhoff, proved that every holomorphic n-dimensional bundle over P1 is a direct sum of line bundles, and the order is the only thing. It is independent of the order, and I want to prove that. But now, of course, will be line bundles which are indexed by the irrationals, not by the integers. So this is the definition of what I mean. Well, this is just, you use power series to define what you mean. Matrix value is cocycles to clutch, so I go fast. So this is the definition. You have to give me a holomorphic map from the annulus to Cn and the clutching map. And now I told you, in order to say, what I want to do, I told you that S1Q for me is now my version of the circle. in fact, I could take any one-dimensional compact solenoid, abelian solenoid, that into one-to-one corresponds with subgroups of the rationals, which are dense. Of course, the ones that are cyclic are correspondent. So this is the, and well, if I want to have this this metaphor, I consider the Adelic group as a set of all continuous maps from this solenoid to a Lie group. And then I worry about what topology I put, what do I do, etc. The point is that this is a topological group because I want to define the loop group, but I want to define the Adelic loop group and see how far I can go with this idea of replacing the circle by a solenoid. Where, well, this is what we are interested in, the Adelic loop group. And here we have this interesting thing. Any map from the solenoid to the linear group can be actually homotop to the first to the unitary group and then to U1 and to this, and therefore homotopy classes are in one-to-one correspondence with mass from the solenoid to S1. We know that that's Q by the theorem of Schaffer because homotopy classes are represented by homomorphisms, and therefore I can talk about characters. I can replace any horrible map by a beautiful thing, which is a character. And this is the proposition. The group of homotopy classes of loops is isomorphic to Q. And thus the connected components of these are in one-to-one correspondence to the additive group Q. And then let's see, let me see a little bit more. Well, now, if I have a map into GLC, if I take the determinant, in the same way I do in the case of P1, I have a map. If I take the determinant, I have a map from the annulus to the puncture to C star, and therefore I can take the winding number, and this gives you the determinant loop, and this will determine the determinant bundle of that. So you have a line bundle, which is when you replace the map to the full linear group, you go to the determinant, and you have a multiplicative. So exactly the same thing you do in a course of holomorphic vector bundles over P1, you do here. Essentially, we're replacing the integers by the rationals. And now, well, now I would like to define, you see, in the work of Presley, Segal, well, even Karen Lulenbeck, etc., the loop group plays a very important role in many things. And something which is very interesting is that the loops into a Lie group have energy. And the energy is the integral of the norm. But I want to replace you see, I want to replace in the circle, you have the line element ds. And I want to replace that by the hard measure on the torus. So first of all, I want a special class of maps. Maps from the solenoid to the Lie group such that belong to L2. Well, here, let me. So the functions of Sobolev space are characterized by Fourier analysis. F is in L2, and F prime is also in L2, where F prime is the weak derivative. So, well, you use analysis, and this is the important thing. The product of two Sobolev functions. So I'm taking Sobolev functions of the solenoid to the Lie group. And this is a Banach algebra. Multiplication is close on the multiplication. And then, well, you consider exactly the Adelic group. So map the identity to the identity. The Lie algebra are mapped into the Lie algebra, exactly like in the case of the loops. Exactly, almost verbatim, like in the work of Segal and Presley. And well, let's see. Let me go faster because well, important thing. Forget all the previous. I take Sobolev because the base Adelic loop space maps of the solenoid into the Lie group that send the identity of the solenoids to the identity of the Lie group is a connected real analytic Hilbert Lie group, which in addition to that is an infinite dimensional holomorphically homogeneous complex Kerr manifold model on the loop algebra. This is true for the standard loop group, maps from the circle to the Lie group, and now from maps to the solenoid to the Lie group still holds. And well, this is in terms of Fourier series, we can define. This is what I tell you. Can define a symplectic form, and this is the important thing. Here plays a very important. You see, for the loop space, you use ds over S1. ds is the length element, the arc element of the circle. Here I use this is the novelty. Here I use the hard measure as a replacement of the hard measure on the solenoid as a replacement of length. And therefore I have this symplectic form. I have this complex structure in terms of coordinates. Here you have that J square is the identity, you can check. So I span in Fourier series the solenoidal loops, and I write as before the symplectic structure, the complex structure. The complex structure satisfies is indeed integrable. There's a theorem complicated by Penon. And so it's integrable complex structure. And the Keller metric is the usual relation between J, symplectic form, and this is the explicit Keller metric. And well, I forget. So this is the, forget it. This is the important thing. Okay, so this manifold is an infinite-dimensional Keller manifold, just like a standard loop space. But now you have an energy function. You see, this is the Dirichlet energy. And for the circle, here you use ds. And here I use the hard measure. And the energy is beautiful in this loop space, solenoidal loop space, will behave like a Morse function, exactly in the spirit of Presley, Seagal, and it will be a Morse function, and the stable manifolds will give you the Birkhoff factorization. And well, I'm almost finished. I'm jumping a lot of things because it's technical, but I'll give you the ideas. The idea is replace the length by the, see, here it is. Yeah, so you can define the energy. And now finally you have the Birkhoff factorization. Maps from the solenoid to the general linear group factorized like that, where gamma minus means that only negative rationals appear in the Fourier expansion, and only positive appear in the Fourier expansion. And this has, and these are characters, and therefore are corresponding to n tuples of rationals. And this will play the role in the Birkhoff-Grothendieck of the Chern classes. I mean, the vector bundles over P1 are classified by n tuples of integers, and here will be n tuples of rational numbers. And by the way, here I also have the infinite Grassmannans, many things. Finally, this is the Birkhoff-Grothendieck theorem for the solenoid. So for me, I'm not scared. Has two horrible singularities, I don't care. For me, it's P1 laminated. So given a holomorphic vector bundle, which I define correctly, of rank n over CP1, there exists an n tuple of, he should be Q1. It's a mistake, Q1 to Qn, such that is holomorphic isomorphic to the direct sum. It's exactly the analog of Birkhoff, but in the case of, I think that's all. I think that's it. I'm finished. Thank you very much.
Thank you very much. Is there any question or comment? So can I say something about, I mean, vector bundles on CP2, for example? Other vector bundles on CP2, yeah, similar.
Exactly. Very good question. Well, this actually proves rigidity for the solenoidal. But for P2, the very good question. I put it in my paper as an open question. I don't know. And maybe there are these theorems that vector bundles over P2 have moduli.
Yes.
And it's a very interesting question but I was not able to to resolve. And also in the spirit of now it's a little bit popular a la mode perfectoid spaces. So my question would be, I don't understand. I understand epsilon of perfectoid, so I shouldn't be speaking about that. But just the words are the same, p-adic. So is there a perfectoid version of what I'm doing? That's my question for Pn. But a very good question. I don't know for Pn the result. And I don't know, for instance, if I take I mean, what about Hodge theory? I mean, you can do the ramp theory on solenoidal manifolds because they behave like manifolds this way, Cantor say this way. That's the best definition of lamination. So you do analysis this way, you algebraic geometry this way, and you see, because Z hat, the profinite completion of the integer, is a compact abelian group, has a measure, hard measure, and that's what I use all the time. The holonomy of these laminations is actually translations in an abelian Lie group. But I don't know the question to the answer. I know the answer to the question, sorry. No tienes computadora, ¿verdad? Sí.
Maybe you speak on both.
Maybe you type it in the chat.
I'll call him on the phone. I'll call him.
Se oye muy mal, ¿eh? No se oye nada.
Okay. Okay, anyway, then.
I can't hear anything. I can't hear.
So, yeah. Yeah, well, I think.
Well, send me an email with a question, Ernesto.
I will.
Okay, thank you very much for your attention.
Yeah.
Thank you.
Thank you very much.